All right, we're gonna get started here real quick, and if you hear popping noises in the background, that would be the fire in my stove downstairs in my basement as I record this. So it's toasty warm where I'm at. Anyways, we're gonna talk today about weight and normal force, given the symbols Fg as well as Fn. Fg standing for weight, and that has to do with the fact that weight is basically the force pulling towards the center of the planet, which we're going to normally say is down. Force pulling down on you because, settle down there, of the gravitational pull of the planet. So weight is equal to Fg, which is equal to mg. On your formula sheet, I believe the formula is given in the form G is equal to Fg over m, where in this case finding weight, m is the mass of the object in kilograms, and G is the gravitational field strength in newtons per kilogram. Now on Earth, what you're going to notice is that gravitational field, I think, well, wait a minute, that doesn't look like newtons per kilogram. So let's just go back a little bit to this and say, well, what was a Newton? Well, a Newton, if we recall back to our Newton's laws lessons, was a kilogram meter per second squared. Right, so that's the Newton part, and then we're dividing this whole thing by kilograms. Right, and some of you already will see, kilogram meter per second squared divided by kilograms. I'm going to end up with meters per second squared, but just if you want to see a little bit of the weeds of the math here. And again, this is one of those, in terms of looking at a unit, it's hard to imagine what a kilogram meter divided by seconds squared times kilograms is. That's why we don't usually think of it in terms of these units. But kilograms divided by kilograms, we end up with meters per second squared, which means our acceleration due to gravity is always going to be our gravitational field strength, because newtons per kilogram is the same as meters per second squared. Now, what this actually means in terms of weight is that when we talk about our G, that is giving a sense of how strong gravity is pulling on us. How many newtons is it exerting on each kilogram? And again, on Earth, it is 9.81 meters per second squared. The easy, estimate is weight is equal to kilograms times 10, because 9.81 is pretty close, so we can get a decent estimate there. Anyways, mathematically, this is something that's kind of interesting to see how the units work out, and that's why we don't have to do a lot of that work, at least not right now, but the unit analysis is a useful tool to have in our belts. So, continuing on. Maybe. There we go. Mass doesn't change, right? We can take a 5 kilogram block and put it on the Earth or on the Moon, and the mass is the same. It is still 5 kilograms. Now, we'll notice on the Earth, the gravitational field strength is 9.81 newtons per kilogram. On the Moon, 1.60 newtons per kilogram. Which means that this block's weight on Earth is 5 times 9.81, so 49 newtons. On the Moon, 5 times 1.60, or 8 newtons. Notice that these blocks also are not to scale. It would be a pretty impressive feat of engineering to have a block which looks like it is roughly the size of like Europe, that only has a mass of 5 kilograms and is still rigid. Anyways, we're leaving that alone. Have not to scale on purpose. Alright, so moving on. Again, weight, fairly self-explanatory, and also it is something that is pretty easy to look at as something that I think you would have learned in Science 10. Normal force, we will come to in a minute. It's a little bit more work, but not a lot. So this is the type of a question you could see. Oops. So we've got a 350 gram mass pulled upward with a force of 8.7 newtons, moving at a constant speed of 6 meters per second. What is the force due to air resistance? So we can draw a picture of this here. Now, we're moving at a constant speed, which means the net force is 0 because there's no acceleration. And this is something to look for, right? If you're seeing constant or you're given a steady velocity, usually it's going to be constant is the word that we'll use, but any word where we say speed or velocity is not changing, that means that F net is 0. Which means when I take all 3 of these forces and add them up, I will get 0. Alright, so we're going to F, and this is the, no, it is the upward force. We usually put applied rather than a U for potentially obvious reasons. Force applied plus the force of air resistance plus the weight of this object, so we'll put it down here as Fg, is equal to 0. Alright, now we know what this applied force is. We know what we can figure out what Fg is, because we are assuming we are on the Earth. We do have to be careful though, this 350 grams, that's the units we're given. We need to convert this into kilograms. 0.350 kilograms. And then we can figure out what mg is. We're going to just substitute that into our big formula here in a moment. So we are saying that up is positive, down is negative. And so we want to know what air resistance is. So we're going to leave that on this left-hand side. And we will come up with F AR is equal to, well, we're going to subtract the applied force and the force of gravity from this left side. So we'll end up with negative applied force minus Fg, which in a moment we're going to substitute that out for mg because that's what it's equal to. And so our force of air resistance, which my computer is struggling with, there we got it almost caught up, is equal to negative, well, 8.7 newtons. Minus Fg. And so in this case, Fg is going to be equal to mg. So it is going to be equal to 0.350 kilograms. Times 9.81 newtons per kilogram. Alright, and so we start working this out. Now, what we're going to see here right away is 0.350. Oops. Try that again on my calculator. So we've got 8.7, that is a negative number, negative 8.7 minus 350 times 9.81. As soon as we see that, we're going to see something funny. We get negative 12. And that doesn't make sense. And so what we actually have to realize is that this 9.81 that's here is actually, because it's going downwards, we need to tell our equation essentially that this is a negative. And so this is going down. And so when we actually end up doing this, we're going to have negative 8.7 minus, and then it's going to be 0.350 times negative 9.81. And we end up with an air resistance force. So force of air resistance, if you'd rather, of negative, well, my calculator spits out negative 5.2665. Newtons. Now, if I looked back at significant digits, I have 2 here, so my answer should have 2. So it is going to be equal to negative 5.3 newtons, or I could say 5.3 newtons down. And now, you might ask, how do you know just by looking at that first answer that it's supposed to say down? And I apologize, but I'm not going to redo it right now. How do I know that that negative 12 business was wrong here? Well, whatever numbers I have here, this number, this air resistance, plus the weight, have to add up to equal 8.7. Because basically this force is pointing up, is used to pull it up. These two forces are resisting that, and because it's moving at a constant speed, the net force is 0. And so if I end up with a number down here that's negative 12, well, the only way then is that if this thing has a negative weight, which doesn't make sense because anti-gravity is not a thing. At least not on the Earth, and we're not dealing with it now. So, that all being said, negative 9.81. Continuing. Come on. Computer's struggling. There we go. All right, so this is the work you would see printed in your notebook that I've handed out to you. All right, so the normal force. Normal force is the force that results from pressing two surfaces together. In this case, we've got this guy pressing fairly lightly on the wall. This person, in this case, he's pressing bigger. The more force you exert on, in this case, the wall, the more that it's pushing back at you. And if it didn't push back at you, you would be pushing through the wall. And so if you're going into, civil engineering and things like that, one of your jobs is making sure that walls and stairs and floors and beams and bridges and all sorts of other things can stand up to the forces that people exert on them, which means that they're able to exert a normal force back at whatever force is exerted on them. Right, and so this is a normal force. Oops, there we go. Normal force, we can measure it, at least if you're standing on the ground, with a weigh scale. You could measure it, I suppose, on a weigh scale on the wall. We're going to get to situations where a weigh scale would be a little bit weird to use, and you'll see those in a bit. But we use normal force also later on when we get to friction, so it's an important thing to be looking at. Now, in this case, this weigh scale probably looks like it's measuring in pounds. We will measure in newtons and not in pounds. All right, so normal force is always perpendicular to the surface. So in this case, the ladder is resting against the wall. The normal force is being exerted by the wall perpendicularly out towards the ladder. The ladder is also resting on the ground. Normal force, the ground is exerting perpendicularly up towards the ladder. Skier is going down the hill. Now, my green arrow did not line up properly here. Also, the one ski looks like it's below the surface of the ground, but, we won't be too picky. And so whenever we write the normal force, it is going to be perpendicular to the surface. So if the circus or the surface at the circus is at some kind of 45 degrees, the normal force will be 90 degrees away from that. and it's always from the surface towards the object. Alright, so here's a kind of a question we could end up. Person with a weight of 700 newtons is on an elevator that is accelerating downward at that rate of acceleration. So that's going to be a negative number. If this person is on a weigh scale, what is the reading in newtons? So your job is to sketch a force diagram and then to state the law and equation. So this is going to deal with Newton's second law because we do have accelerated motion. If we look at the person, there's two forces at work on the person. There is the force of gravity pulling them downwards. And we also have the normal force pushing them up. This is stopping them from going through their weigh scale or the floor of the elevator. So in terms of how this works out, we set it up this way. And in this case, they're saying down is going to be positive, up is negative. You could easily set it up the other way, but that's how I'm going to set it up here. So we're going to say F net is equal to mass times acceleration. Now what this does mean is we are going to have to figure out what this person's mass is. Now, if you remember, Fg is equal to mg. We know what g is. Mass is going to be pretty close to 70 kilograms, but we need to find what their actual mass is because we need to take their mass times this acceleration. So that's going to be kind of our first step once we're ready to actually solve this problem. Now, the net force is going in the downward direction. And so we're going to be taking our Fg minus the Fn is going to be equal to whatever that downward force is going to be. Oops, sorry. Now, this is how it's set up in your notes. I don't like how the negative shows up there because this is not the way we've been discussing it. And I borrowed these notes from somebody else. I'm going to be changing a few things going forward to make it so that it's all consistent. So I've rewritten it here. This is what we're going to be redoing from here on out. We're saying Fg plus Fn is equal to the net force, right? This force pulling down plus this force pushing up is equal to the net force. Now we're told that the net force, so that the acceleration is downwards, which means the net force also has to be downwards. All right. Now, in terms of figuring out the mass, that work is shown right down here. Mass of this person is going to be 700 divided by 9.81, and we end up with 71.356 kilograms. We're going to use that unrounded value when we start checking it over here. Mathematically, what's going on here? Well, this force pulling down plus this force pulling up is equal to the net force acting on the person. So let's take a look at it. We want to find what the normal force is. That was the question originally asked, which is going to be the net force, or the mass of the person, 71 kilograms, times the acceleration of the person, 5.8 meters per second squared downwards, minus the force of gravity. All right. So let's take a look here. And again, to show that it works to do this in a different way, we are using down as being positive and up as being negative. So we're going to assume probably we're going to get a negative answer here. So let's go. So normal force is equal to, well, we figured out the mass over here. 700 divided by 9.81, lovely, it's 71.536. Computer issues. Kilograms times the acceleration of 5.8 meters per second squared. Again, if you look at units here, if we're thinking unit analysis still, units are going to be kilogram meter per second squared. Oh, this is newtons. Okay, good. Minus force of gravity minus 700 newtons. This so far is making sense. We're going to have newtons minus newtons. That's good. And that's going to give me an answer here for my normal force, which punch into my calculator here. 71.536 times 5.8, 414 number, minus 700. We end up with negative 285.0912. And I used the wrong number here. I just realized I got the wrong answer. 71.356, not 536, times 5.8. So I wrote the right numbers down on this. I didn't even do that. Good grief. 3, 5, 6. There we go. Times 5.8, 413. That's going to be the right answer. It'll be 286 instead of 285. So normal force is negative 286 newtons. Now it is 0.1352. And if I look back at my question, actually, it's negative, which means in this case, given our system of references, that's up. 2 significant digits here. So this is annoying, but our normal force is equal to 2.9 times 10 to the 2 newtons up. And there we are. What this means, of course, is that this person, as the elevator is moving down, feels lighter than they actually are, which if you've ever been on a fairly quick moving elevator, especially when it starts and it's going down, you kind of get that whooshing sensation in your stomach. Not quite maybe like you'd have in a roller coaster, but that's the idea. Right. Moving along. Maybe. There we go. Again, this is the work that you'll see in your book. Pretty much the same as what I just did here. A little bit neater because it was on the smartboard and not the computer screen. And this is how we fixed it in the notes. Alright, so this was the solution given there, and you can see everything is good except it's sort of ignoring the negative signs, and I want to be consistent, and so we're not going to use this page and get rid of it. Alright, so now your job here, compare the weight and normal force for each. We've got a person on a scale, same person on the same scale in 4 different elevators, and we'll look at each of them in turn. So we've got 4 meters per second moving upwards, 5 meters per second squared accelerating upwards, 6 meters per second squared accelerating downwards, 9.81 meters per second squared accelerating downwards. All right. So for the first one, acceleration is 0. What that means is that the net force is 0. This means Fg plus Fn, the normal force plus the weight, is 0, which means Fg is equal to the negative of the Fn, or the magnitude of Fg is equal to Fn. And if you're used to absolute value notation, we can put the absolute value notation here just to show that the numbers are the same if we disregard negatives. All right. Moving on to the next one. In this case, we're moving upwards. There is a net force. You are going to feel heavier. And that's because you are being accelerated upwards. Your body resists that, pushes down into the floor, which means the weigh scale shows a heavier weight. And that means that the floor is having to push back up on you extra hard so that you don't go falling through. If the elevator is built properly, you will be fine. This is why there is weight limits for elevators. So, it's funny how we use the word weight for what we're actually referring to as mass limits, really. But the idea here, of course, is if there is a 1,500 kilogram limit on how much mass you can put in there, what that means is that the floor is definitely able to deal with the acceleration of that much mass in terms of the normal force. They'll have to be bigger pushing up to make sure that they don't fall through the floor of the elevator. but it won't be able to deal with necessarily a lot more than that. So in this case, the absolute value of the normal force is greater than the weight. You're going to feel heavier, and if you've been on one of the roller coasters that doesn't drag you slowly up the first big hill, but shoots you up the big hill, you would feel this as you accelerate up that hill, as you're going to feel heavier in your seat. Right. In this case, we're accelerating downwards, and so we've just left, and so the elevator is speeding up and moving down. In this case, the normal force is going to be less than the weight, and you're going to feel lighter. And that's simply because as the elevator moves down, it's like it's moving away from you, and so the floor doesn't have to push up as hard on you to keep you from falling through. And then we have this unpleasant situation. We could say the absolute value of the normal force is 0, but if you are accelerating downwards at 9.81 meters per second squared, first of all, this is going to be a bad elevator. Second of all, you are in free fall, which means you're not going to be exerting any force on the floor, which means it's not exerting any force back up on you, which means your normal force will be 0. Generally, elevators are, we want to avoid elevators that are in free fall. And that's where we end here. So you've got the questions 1 and question 6 in your workbook to do over the weekend. Thanks.